Hello guys, so we're going to continue with applications of differentiations. Okay, so all right, let's try this formula here. F of x equals x cubed divided by 3 minus x. Let's find the critical points. Okay, so f prime of x is going to be equal to x squared, okay, because 3x squared, then you have divided by 3, okay, x squared minus 1. That'll be the first derivative. Now, when is this thing, well, let's just calculate the second derivative too. Second derivative equals 2x. Okay. Now, from this, we know that the critical points, okay, the x critical points, let's see, is going to be when x squared minus 1 is going to be equal to 0, because that's when the tangent will be 0, right? It's the first derivative. So x squared equals 1, x equals plus or minus 1. Okay, so we can say that plus minus 1 are going to be the critical points in here. So we have the domains, all right? The domains, okay, that's fine. Domains are going to be minus infinity all the way to minus 1. And then you have from minus 1 to 1. And then you have from 1 to infinity, all right? In here you have the critical point minus 1, and in here you have the critical point 1. All right, so well, let me see here what the okay, let's try this. When x equals minus 2, the second derivative is going to be negative. Okay, well, actually, let me think here for a second. When x is exactly minus 1, because at minus 1, the first derivative is going to be 0. So when x is minus 1, the second derivative is negative, right? Because 2 times minus 1 equals minus 2. Okay, so this indicates that this point here, which is the minus 1, I'm going to put a minus 1 here, and here I'm going to put a 1. This minus 1 is a maximum, okay? What about when the point is 1? Well, 2 times 1 equals 2. So the second derivative is going to be positive at 1. So this point 1 is a minimum. All right. Let's see what else we can think about this. Let's try to pick a number from this interval here. Inside this interval, let's see minus 2. So minus 2 times 2 here in the second derivative is going to be equal to minus 4. So the second derivative is negative. That means the concavity is down, right? Yep, the concavity is down. So the concavity here, well, let me just do this. For this domain here, the the concavity is going down. Okay, it's a downward concavity. Okay, what about here? In this domain here, we can pick, for example, 0. Now, here's the thing, okay? You know, 0 is also going to be a critical point. 0, yeah, well, you see, at 0, the tangent is not, well, okay, fine, we can do that. 0 is also a critical point, okay? X critical is 0. So let me expand these domains in here. I'm going to drag all this stuff to the right. Yeah, all the way up here, just so that I can have some more space, okay? And then I'm going to have another domain from minus 1 to 0, okay? And then you have the 0 itself, and then you have from 0 all the way to 1. Okay. And then you have the 1. Okay, I'm gonna do this. I'm gonna erase this stuff. This one here, I'm gonna put it more like that. I'm gonna try to organize this here, guys. This one I'm bringing here. Okay, I'm gonna erase this one. I'll get this. I'll explain to you guys what I'm doing. Why is x equal to 0 a critical point? Well, the tangent's not going to be 0, but x0 is a critical point because that's a point of inflection. Remember, you got a tangent that's not 0. When x equals 0, the tangent's going to be -1. So you got a negative tangent like this, okay? And the second derivative at x equals 0. That means that it's a point of inflection. Okay, it's changing the concavity here. So this, I'm gonna say it's a point of inflection, all right? Now let's think about this stuff in here. If this is a maximum, if this -1 is a maximum, that means that this concavity has to be, well, let me think. Oh yeah, both. If it's a maximum, this concavity has to be down, and this concavity here has to be down too. This is a point of inflection. That means this concavity has to be up. Concavity is up. Now we're going to check this out. Okay, if from negative all the way to -1, the concavity is down, all right, and at -1, you got a tangent that's equal to 0, so you go like this. This is the point -1 in here. Okay, if this is a maximum, whatever comes next has to be like this. Why? Because if after the tangent becomes 0, you had something like that, it would not be a maximum. For it to be considered a maximum, you have to have something going down here. That means that the concavity is also down, but let's try that. Well, between -1 and 0, like -half. Well, -half times 2 is going to be -1, so the second derivative is negative at this domain. So yes, the concavity here is down. Okay? Which agrees with this. You got a concavity down here and a concavity down here, a tangent of 0. That means that this point is a maximum. And this point right here is the -1 point. X equals -1. Okay. Now you have 0, which is a point of inflection, okay? If it's a point of inflection and you have a negative thing here, you gotta have a positive concavity on the other side, because the point of inflection is when you change the sign of the concavity from negative to positive, or from positive to negative. Is the concavity positive in this domain? Yes, because get a value within this domain like half. 2 times half, that's 1. So the second derivative is going to be positive, the concavity is up. Okay? So this is right. 1 is a minimum. Okay, we already know that 1 is a minimum. Why? Because at 1, the first derivative equals 0, and the second derivative is not equal to 0, it's 2. That means if the second derivative is positive when the first derivative is 0, that means that it's a minimum. Now look at this. So you have this domain in here, okay, which is going kind of like that. And then when it gets to 1, this is x equal to 1 here. I'm going to do this. This is x equal to 1. When it gets to 1, you have a minimum. If you have a minimum, you have to have a concavity up over here, okay? Otherwise, if you were not a concavity up, if you were a concavity down like that, this would not be a minimum. Okay, so you have to have a concavity up. Do we have a concavity up in this domain here? Yes, we do. We have a concavity up. Why? Because pick a value from this domain, like 2. 2 times 2, 4. It's the second derivative is positive, so the concavity is up. All right? So let's get the graph. Now this is the graph from the book, okay? You just gotta worry about the top part, because the bottom part is just the graph of the first derivative. But worry about the graph of the function itself. What do we say between negative infinity and minus 1? Negative infinity and minus 1 is going to be a concavity down. Yes, the concavity is down. At x equals minus 1, it's going to be a maximum. It's a maximum, and the tangent is 0. So the first derivative is 0. That's great. For this domain in here, I said that the concavity was going to be down, and it is, okay, up to this point, well, actually it's up to this point. So all the way up to here, from x equals minus 1 all the way to x equals 0, you got a negative concavity here, okay? Did I say that the concavity was negative from minus 1 all the way to 0? Yes, look at this, all right? Now, you have a second derivative at 0 here. That means that it's a point of inflection. Is it a point of inflection? Yes. You got a negative concavity, and here you got a positive concavity from x equals 0 all the way to x equal to 1. Okay? Did I say here, you see, what I'm trying to prove to you guys is that what we found out all over this place in here is in accordance with this graph here. Okay? Now let's try again. Let me think. Okay, yeah. So let's see. So from x equal to 0 to x equal to 1, you have a positive concavity. Yes, you do have a positive concavity here. I said that at 1 you were going to have a minimum, and at 1 here you have a minimum, and then you were going to have a positive concavity, and indeed you do have a positive concavity after x equals 1, all right? From 1 all the way to infinity. So what we found out here is in accordance with this graph. And that's it for this exercise. Now we got another one. Okay, f of x equals 6 divided by x squared plus 3. It's telling me to find the first derivative, okay? So the first derivative equals, this is 6 times x, so you put a 6 here, times x squared plus 3 to the minus 1, okay? So the minus 1 is going to come down, multiplying here to minus 6. And then x squared plus 3 is going to become, it will go to the power of negative 2, okay? So we have this. All right? And now you have the chain rule, right? You have to differentiate with respect to you gotta multiply to the derivative of the inside function, which is x squared plus 3, which is 2x. So you multiply this by 2x, and what you have minus 12x. So I'm just gonna do this here. I'm gonna get the 6 out, and I'm gonna put a minus 12x. Okay. Great. The second derivative, in here we're going to have to apply the, hold on guys, let me get this organized in here. Okay, the second derivative, since we got a function up and down, we're going to have to use the differentiation division rule. So this is going to be long. Okay, so it's the g of x times the derivative of f of x minus f of x times derivative of g of x divided by g of x squared, or g squared of x. So x squared plus 3 squared times minus 12 minus minus 12x times the derivative of this, which is going to be 2 times x squared plus x squared plus 3 times 2x divided, man, that's big, by x squared plus 3 to the 4th. Yeah, that's something. That is something. Okay, now we can simplify a little. You see, this is like the sum of products. So this is one product, this is another product, and this is another product. You can see that in all the three products you got x squared plus 3, at least one term. So we're going to simplify them. Okay, this one here is out. Forget about this. I'm just going to do this in here. Okay. This 2 here is out, and this one here becomes a 3. Oh, well, so it's not going to be too messy. Okay. Now let's see this. You have, oh man, let me think. Let's do this. So I'm gonna try to multiply this out. I don't know if I should do that, but hey, I'll do it. You're gonna have a minus 12x squared minus 36. Okay. Over here you got a minus with a minus, so everything's gonna become positive. And now you got 24x times 2, 48x squared. This is going to become, okay, divided by x squared plus 3 cubed. So this 48 minus 12 is equal to 36. So it's going to be a 36 in here, and you got another 36 in here. So you got a 36 x squared, yeah, minus 1. Yeah, 36x squared minus 1 divided by x squared plus 3 cubed. Yeah. So this is the final result. I'm going to drag it here. All this mess, all this sketch, I'm going to erase. Okay. Now let's see. What are the critical points in here? The critical points are when the first derivative is 0, okay? So the denominator doesn't have any problems because it's x squared plus 3, so you don't have to worry about it, okay? If you were x squared minus 3, you could not have plus or minus square root of 3, okay? But it's x squared plus 3. This plus says that the denominator is safe. It's never going to be 0. So you don't have to worry about the critical axis where the first tangent doesn't exist. The first tangent always exists in this function. So I can see here that the only thing that's going to make this formula become 0 is when x is 0. Okay, that's the only thing that you got to worry about here. That's the only critical point. Now, let's think about the second derivative. The second derivative, you don't have to worry about the denominator either. Okay, because the denominator here is never going to be 0. The only thing that can make this stuff here become a 0 is when x equals minus 1 or 1. So this is for the first. I'm going to do this. This is for the first derivative. Now the x critical for the second derivative is plus and minus 1. This is for the second derivative. So when x equals plus or minus 1, you're going to have a second derivative becoming a 0. And plus or minus 1 is not going to make the first derivative become a 0. So you know that these 2 points in here, plus and minus 1, are points of inflection. All right. That's beautiful, guys. You know, when math works, it's just beautiful. It really sucks when you work and work and work for hours and days, and after like a week, you discover that you made a mistake someplace and you gotta redo everything. So when math works, oh my God, it's beautiful. Okay, so we have a few domains in here. Okay, domains in here. You gotta worry about these. So the domains are from negative infinity all the way to -1, and then you have a -1, and then you have from -1 all the way to 0, and then you have a 0, and then you have from 0, I mean, it's not exactly from 0, right? All these parentheses here means that the intervals are open, so it's anything from negative infinity all the way, not up to -1, but everything up to -1 and a little bit to the left. Okay, so it's not going to be -1, it'll be minus 1.00000000001, but it's never going to be -1. It can never be -1. -1 is this part here. Okay. So in here it's going to be everything after -1 and everything before 0, and then you got a 0 and everything after 0 all the way up to 1. I mean, all the way up to almost 1, and then you have a 1, and then you have from everything ever after 1 all the way to infinity. Yeah, everything after 1 all the way to infinity. Great. Now let's see. When is the first derivative going to be 0 at 0? Okay, and at this point in here, when x is 0, the second derivative is not going to be 0. But what is the second derivative going to be? Well, this is going to be a -36, and this is going to be over 27. Okay, so it's going to be a negative number. Yeah, it's going to be a negative number. That means that it's a maximum. So this is a maximum. Why? Because at this point, the first derivative is 0 and the second derivative is negative. Okay, how do we know that? Well, plug 0 in here and plug 0 in here. You're going to see that this is going to become -36 divided by 27. So minus divided by plus is going to be a minus, so it's negative. If it's negative, it's a maximum. Okay, so this is a maximum. Okay, if this is a maximum, then the concavity here has to be down, and the concavity here has to be down. Otherwise, it would not be a maximum. Yeah. -1 is a point of inflection. -1, the tangent is not going to be 0, because the only place that the tangent, the first derivative, is 0 is at 0. So -1 is not doesn't have the first derivative as 0 and has the second derivative as 0. So this is a point of inflection. So this becomes a point of inflection. If it's a point of inflection, it's changing. Okay, concavity down here. That means that this has to be concavity up. Over here, 1. 1 is the second derivative is 0 and the first derivative is different than 0. So this is also a point of inflection. And concavity down here, so the concavity over here has to be up. Now let's see if it's really this way. Look at that graph. All right, I'm going to increase it even more. Must be hard for you guys to see it. Okay, so let's see here. From negative infinity to -1, concavity up, and it is a concavity up. You see the tangents is increasing here. -1 is a point of inflection. There you go, -1. Oh man, come on, don't do this to me. Jesus, this is a disaster. Okay. Do this, okay. So minus 1 here is a point of inflection when the concavity starts going down. And from x equals minus 1 to x equals 0, the concavity is down. Concavity is down here. I said that 0 was going to be a maximum. There you go. 0 is the maximum here. See here? It's funny. 0 is a maximum here. Look at that. It is a maximum here. Okay. 0 is a maximum. If 0 is a maximum, everything that comes after the maximum has to be a concavity down, because everything before the maximum was a concavity down too. So yes, you got a concavity down here. You see the tangents becoming increasingly more negative. It's becoming increasingly negative. And then the tangent's still negative here, but it's becoming decreasingly negative. It's becoming less and less negative. That means the concavity is up. And after the 1, yes, the concavity is up right here. See? Over here. The concavity is up. And 1 is a point of inflection. And yes, here is the 1 being a point of inflection. And it just works. See? These things are kind of a pain, isn't it, guys? I mean, it's not... the exercises are just becoming more and more complex. Okay, another one. I think I'm just going to make just one more about this subject, this topic. X squared plus 1 divided by x squared minus 4. So the first derivative equals, geez. Man. Yeah, we're already starting with a bang, huh? Okay, so let's take the first derivative of this. X squared minus 4 times 2x minus x squared plus 1 times 2x. Alright? Oh yeah, divided by x squared minus 4 squared. This is the first derivative, so let me think. Yeah. All we can do here is x plus 2x plus 2x plus 2x. Yeah, we can't do much in here. The only thing that I can do here is factor out the 2x. So it's going to be 2x. I don't know if I should do this. Yeah. The book isn't doing that. The book is multiplying it out. Okay. Okay. Let's do this stuff. Let's worry about the x cubed up here. The only way that you can get x cubed is by x squared times 2x. And over here is having minus x squared times 2x. So it's going to be 2x cubed minus 2x cubed. They're going to cancel out. Okay, then you have minus 8x plus 2x, so it's going to be minus 6x. Yeah. Minus 8x plus 2x. Oh yeah, it's minus 8x plus 2x, but then you have a minus here, so it's minus 8x minus 2x, which is minus 10x. So it's going to be minus 10x divided by x squared minus 4 squared. Yeah. This is the first derivative. Okay. Now, gotta do the second derivative. So, x squared minus 4 squared times minus 10 minus 10x times the derivative of that, which is going to be 2x squared minus 4 times 2x all of this divided by x squared minus 4 to the fourth. Now, here we can simplify a little, okay? We're gonna do this here. This, you see, you got a x squared minus 4 here, x squared minus 4 here, and x squared minus 4 here. So let's do this. This x squared minus 4 is gone. Why? Because this squared here is gone. And this, I'm going to substitute with a 3. Okay. So let's try to multiply this out. This is going to be minus 10x squared plus 40. And here, everything is multiplying, right? So it's going to be a positive number here. So it's going to be 20x plus 40x squared. Okay? 4x times 10x, 40x squared. Alright, divided by this. So 40x squared minus 10x squared is going to be equal to 30x squared. Yeah. So it's 30x squared plus 40 divided by that. I'm going to put that later. I'm just trying to think here about something. Okay, so I'm thinking about something here. Yeah, so I can factor out the 10 here. Okay, so it's gonna be 10 times 3x squared plus 4 divided by x to the fourth, x squared minus 4 cubed. So we get this, put it here. Erase everything else. Okay, now let's find the x critical for the first derivative. Okay. So when x is going to be when x is 0, what else? When x is plus and minus 2, why? Because when it's plus and minus 2, the denominator is going to be 0 and the numerator is not going to be 0. So it's something that doesn't exist. The first derivatives that don't exist, you gotta worry about them too. So minus 2 and plus 2. Okay. For the second one, for the second thing here, I'm sorry, second, yeah. The x criticals, let's see. What's gonna make it 0? Well, yeah, I'm thinking here. So minus 2 and plus 1 is also going to make it minus 2. Yeah. Minus 2 and plus 2 is also going to make the denominator 0 and the numerator non-zero. So these are already here. Okay. And what about the numerator here? When is the second derivative going to be 0? Well, let's see. So you have... What I'm going to do is to equate, okay? And, just worry about the numerator. Forget about this, okay? I'm just worrying about the numerator. When is the numerator going to be 0? Well, 0 divided by 10 is 0, okay? So what you have is 3x squared equals to minus 4. And then you have x equals to minus 4 divided by 3. And it's going to be the plus or minus square root of this. So it's going to be a square root of a negative number, which is this equals plus or minus 2i divided by the square root of 3. because I is the square root of -1. This is a complex number. Yeah, the book is not worrying about the complex numbers. Okay. Yeah, the book is definitely not worrying about the complex numbers. So I'm just gonna erase this, and I'm gonna erase this stuff, and I'm just gonna erase this stuff in here. All right, so let's worry about the domains. The domains are gonna be from -infinity all the way to -2, and then you have -2, and then you have from -2 all the way to 0, then I have 0, then you got from 0 all the way to 2, and then you have 2, and then from 2 all the way to infinity. All right, now let's see. Let's see here, when it's -3, let's get something from this domain. Okay, you got a -3 here. This is going to be positive, and this is also going to be positive, so you don't have to worry about that. Okay, yeah, the only thing that I gotta worry about is this. At this point here, -2. Okay, let's just think about this. So you have a positive plane. Okay, here's something that you don't see every day. So you have a positive tangent here, okay? You got a positive tangent at this domain. When x equals -2, the first derivative approaches infinity, okay? Infinity. Why? -10 times -2 is going to be 20 at the first derivative here, okay? And this is going to be 0 because it's -2 squared, 4 minus 4, 0 squared, 0. So this is going to happen. This approaches infinity, positive infinity. So you can see that the graph, let's do this big. Okay. So you can see that the graph, let's put a kind of a, let me think here, guys. No. So I'm gonna put like a 2 here. Okay. And I'm gonna, yeah, this is a x equals -2, and here it's like x equals 2. Okay. So x equals -2 here, x equals 2 here. Right. So when it's approaching from the right, from the left, -2 from the left, it'll reach positive infinity. Okay, and there's something else that you guys are going to get later. You see that, so it's going to be positive infinity like this. Okay, but what is the graph going to do over here? Well, you can see that as x becomes negative infinity, this is going to be a negative infinity times -10, it's going to be a positive infinity, and then you have an x squared here, which is going to be a positive infinity, blah, blah, blah. But you can see that the power of the numerator is 1, okay? And the largest power of the denominator is 4 because you have an x squared here, squared. So it's going to be x to the 4th. That means that this to the negative infinity is going to reach a limit of 0. So the graph is something like this. And this thing here is an asymptote, okay? So the graph is gonna infinitely approach this stuff, but it's never gonna actually touch it. Okay. What about this stuff in here? What about approaching -2 from the right? Well, let's try, for example, and -2 from the right. Okay, let me think here, like -1/2 or -1.9. So this is going to be positive. Okay, and this is going to approach 0. So it's also going to approach the thing. Well, let me think here, guys. Let me think. Let's try if it's -1.9. So this is going to be positive, and this is going to be, oh yeah, this is going to be negative. That's right. Right. So it's going to be negative. At 0, the first derivative is going to be 0, and the second derivative, negative here and positive here, so it's going to be negative. It's a maximum. Yeah, there are so many things to analyze. Okay, so here we go. If you do like, let's put a minus, because it's got to be something between -2 and 0 approaching 2. Okay, so let's put something like -1.5. -1.5 is -3 divided by 2. So let's do this here. Over here, -3 divided by 2, so it's going to be 30. It's going to be 30 divided by 2 divided. This is in the using this formula, the first derivative. Okay, and here you got 3 divided by 2, so it's going to be 9/4 -3 divided by 2 squared, 9/4 -4. Well, this is the same as you put this in here, and it's -16. Okay, I'm just taking a minimum common denominator. 9 minus 16 is going to be -7. So you got a positive here, and you got a negative here. Okay, and as it approaches 2, it approaches either positive infinity or negative infinity. So it's going to be negative infinity. It's going to be like this. Now, where is it going to go? Well, yes, we're in this domain here. We're analyzing this domain here now, okay? This domain here. Okay, now it's going to be at 0. Now at 0, the first derivative is going to be 0. So it's a flat line tangent, okay? And the second derivative, just plug in a 0 here, it's going to be 40. This is going to be 0 minus x cubed is going to be -64, so it's going to be 40 divided by -64, which is a negative number. If it's a negative number in the second derivative and 0 in the first derivative, that means that it's a maximum. So it has a maximum at 0 here. At 2, it has to approach minus infinity. You know why? Because 0 has to be a maximum. If the graph does something like this is not a maximum. Okay, so you want it to be a maximum, the graph has to do this. It just has to. All right, now you can confirm it. Plug in, for example, 1 over here in this formula, in the second thing. Okay, so 1, this is going to be positive, and this one here is going to be negative. So in this domain, the second derivative is negative. If the second derivative is negative, it's concave down. And this here is concave down. So we're right. At 2, it's just going to be an asymptote. Okay. Now let's try to put 3, which is analyzing this domain here, to see what the graph does. Okay. 3. I'm going to plug in 3 here. Okay. So at 3, it's going to be like 10 times 27 plus 4, that's 31. Divided by 3, okay? which is going to be 9 minus 4, 5, divided by 3, 1, 25. So the second derivative is positive. If the second derivative is positive, the thing has to be concave up. But it has to approach infinity as it comes close to 2 from the right and the left, okay? Because when you have asymptotes, it approaches infinity and it has to be concave up. If you do this, it's going to be concave down. So I know that the graph has to be like, oh yeah, and there's something else too. You see this here? The largest power in the numerator is 2, and the largest power in the denominator is 6. Because this is x squared cubed. So the denominator is a lot larger, has a lot larger power than the numerator, so I know that the graph is going to do something like this. It'll approach 0, okay? Or it's going to approach some kind of number. Yeah, it may not approach 0, okay? This doesn't have to be 0. Maybe it's approaching something else, and we're going to study that later when we study limits. So look at this graph in here. I'm going to put this graph kind of over here. I'm going to put the graph here. And then I'm going to get the graph from the book. And see, it really looks, it goes up in here like that. So it's going up in here. And then it has an inverted U. You got an inverted U. And then you have something like that and something like that. Now you can see that it's not approaching 0. Maybe it's because the graph is too short, it's too narrow on the horizontal axis. Maybe it is approaching 0, maybe it's not approaching 0. And the way we're going to find that out is when we go to limits and we start actually here, because it's x squared, the function that makes this graph is x squared plus 1, x squared minus 4. Okay, so just for you guys to understand, we can do a limit as x approaches infinity and minus infinity like this. You have this function, okay? I'm going to copy it over here. So you got this function here. What you do is that you want to divide everything because the powers are the same, okay, in the numerator and in the denominator. So the limit exists, and the limit is well, in this case, it's a rational number, but it does exist. What you got to do, you want to divide every term in here by x squared, okay? So, x squared divided by, yeah, I'm just going to do this. Divide this x squared by x squared. What do you have? 1 plus 1 divided by x squared. Everything x squared in here divided by x squared, you got a 1. Minus 4 divided by x squared, okay? Now, check this out. As x approaches infinity or minus infinity, okay, this number here in the numerator, and this number in the denominator, and this number here in the denominator are going to be so huge that 1 divided by that, this is going to approach 0. And this thing here also is just going to approach 0. So what do you have? You have 1 divided by 1. So the whole thing, as x approaches infinity, okay, and because it's x squared, so minus infinity times minus infinity is going to be positive infinity. Okay, as x approaches infinity and as x approaches negative infinity, the graph is going to approach 1 divided by 1, which is 1. And look at this here. This stuff over here, guys, look. Oh man, that's not what I meant to do. This. Look at that. You can say that this line is an asymptote of y equals 1, okay? So you have a graph that approaches that line forever. It's never going to touch that line, but it approaches that line forever. But I'm just getting ahead of myself. I'm going to finish this video, and maybe I'm going to make some more exercise on the next one, but for this one, that's it.